I'll share the solution for the midterm, but we'll anyway go through the solutions in class 1. See, I thought some of the questions, some of you answered well, but there seems to be confusion about this inner product thing. The first three questions, I don't think I have to go through because those are just definitions. So you simply have to, if you've got it wrong, you have to go back and look at the definition. And then this question of whether uh, matrices of this form or the set of matrices of this form, which is simply your 2 cross 2. The question was whether this is a vector space. Most of you got it right. This is a vector space. And in fact, we discussed this in class as well, right? When I talked about matrices, I said matrices in general form vector spaces, and that the notion of a vector is a general one. It's not just a column vector of a column of numbers that are vectors. Vectors are general elements. And if you ask me what is a vector, vector is simply an element of a vector space. And what is a vector space? Vector space is a set that is closed under um, scaling and scalar multiplication and addition. Right. So any set that satisfies scaling and vector addition, then and the elements of the set would be called vectors. In fact, there was in one of the classes we even discussed that the set of polynomials of this form, set of polynomials of x of order less than some finite value. Let's assume x. If you have a set of polynomials like this, and if you define a scalar multiplication operation and the addition operation of two polynomials, right? And if that set is closed under these two operations that you define, then this is a vector space. In fact, this is the set of polynomials of finite order uh, is in fact a vector space. The next one. Yeah, and then this idea of see, in fact, this was defined as question 5. No? Question 5, yes. This was defined as a function like this. Right? What does this mean? So if you see something like this, what can you say about this function in words? Yeah. So, sorry. No. Forget about inner product. If you see a function definition like this, what can you say about the function? What do you know about the function? No. See, I'm not defined any operation. I've simply said, here is a function. Exactly. This function takes in two cross two matrices, and returns a real number. You can give it to them. Right? That is all this means, right? That means whenever you take two matrices A and B, where A and B are two cross two matrices, what is the outcome of this operation according to this function definition? It's a real number, right? Because that's what it's defined to be. It takes two arguments, both of them are two cross two matrices, and what it returns is R. Well, what it does with these two to return a real number, we'll get into that later. But this definition itself simply says what goes into the function. If you think of this as a black box, what goes in are two cross two matrices. What comes out is a real number. And then later on, I do define what exactly this operation means, and it's defined to be like this. Now, this is A11, A12, mhm, and B11, B12. And this operation is simply okay. Okay. What am I actually doing uh, in this function in words? Some of what? Okay. Which element? There are four elements though. Is it all possible combinations? See, all you're doing here is multiply these two, these two, and then you add them together. That's all. And then this whole thing is a real number. Yeah. So now, and and the question says that this is the standard inner product of the vector space R to cluster. And then you are asked, okay, if we now define a norm, so if this is a standard inner product, we can define a norm which is simply the inner product of a matrix with itself. The question was whether this is a valid norm. All you had to do was check if the three or four properties are satisfied by this with this definition. Okay. See, in fact, if this was returning a matrix, right? This whole thing returns a matrix, but a norm returns a non-zero, sorry, non-negative real number. Yeah. So this many of you missed. So in fact, you will find that this is in fact a valid norm, and this is in fact equal to what? We've seen this before. Square of the Frobenius law. Okay. So what is the Frobenius norm of a matrix? Do you remember? So if you have A, what is the Frobenius number? Simply the sum of the square of the individual elements. Is it clear? So if something is not clear, you should ask me now. Okay, I'm assuming this is okay. Yeah. And then the next question was about the set E that had these four matrices. And then the question was whether or not this is a linearly independent set. All you have to do is verify the condition for linear independence. What is the condition for linear independence? Uh-huh. So you take the linear combination of these, and the linear combination of a set of elements is simply each of these elements multiplied by some scalar. And if you do this, what you get is this. And this needs to be equal to 0. And we need to find under what condition is this equal to 0. Okay. The only way the first element can be 0 is if it's alpha 1 is 0. And same for all of them. That means the only way the linear combination of these four elements of the set E will give me the 0 element. Okay. 0 element of R2 cross 2. Okay. Is if each of these scalars are 0. That means this is a linearly independent set. Okay. But that's not done though. So the question is whether this is the basis for R2. Not R2, R2 cross 2. We've only shown one condition. Does it span R2 cross 2? How do we show that? What do we mean by does this? What do we mean the span of? Well, we need to go back to the diff. What is the span of? No, no. I'm asking you what is the definition of the span of the set E? Yes, okay. That's this, right? Any linear combination of this set E looks like this, right? So the set of the span of E is a set of elements that look like this: alpha 1, alpha 2, 3, alpha 4. And what are alpha 1, alpha 2, alpha 3, alpha 4? These are real numbers. What is the definition of the 2 cross 2 R2 cross 2 set? Well, four numbers arranged in a rectangular form where each number is a real number. That's exactly this. That means the span of E is in fact R2 cross 2. That means it is the basis for 2 cross 2. Some of you got this right, so that's okay. The next one was, does this form an orthonormal basis? How do you check? So we know it's a basis, right? So you use the result from the previous uh, question uh, to develop to come up with the answer for the next one. The question is, we know it's a basis. Now, is this an orthonormal basis? How do we find out if it's okay? So if we say inner product, you have to first know what inner product. The question already says the standard inner product for this space is this, right? So how do you verify that now? All you have to make sure. So, well, if that's the standard inner product, right? Um, okay, let's go back. What is the definition of an orthonormal basis? When is a basis orthonormal? Sorry, what? Not matrix, right? Each element from the basis set, right? See, the orthonormal basis is a set, okay, which is a basis. Okay, this basis has this additional property of being orthonormal under what condition? One of the conditions is what you said. Each element of this basis should have length 1. Okay, but again, length 1 according to which norm? That we'll come to later. And that's 1. What is the second condition? Orthogonal to what? Right. Each element here should be orthogonal to every other element. That means here there are only 4 elements here. The first thing we have to make sure is that all of them have length 1. Okay, how do we? Well, we know what the standard inner product is. We have the norm induced by the standard inner product, so we'll use that as a measure of length. Right? Is the is What is this according to? Is this equal to 1 or is it greater than 1? Well, it cannot be 0 because these are not 0 matrices. This is equal to 1. What about? In fact, all of them will be equal to 1. The length square, or here, this is equal to the square, so its length square are equal to 1. That means the length is 1. So the first one is satisfied. All of them have length 1. What about this property of being perpendicular? Is uh, this element perpendicular to this, and similarly this perpendicular to this, and this perpendicular to this? That means we have to verify. Yeah. What will this work out to? It'll work out to 0, right? Here, all you're doing here is multiplying the corresponding elements and adding them together. This is 0, 0, 0, 0. So this will be 0. And in fact, if you check the inner product of any of those, you will find it's all 0. That means they're all orthogonal to each other. Okay? So in fact, both the conditions are satisfied. So it is in fact an orthonormal basis for, it's not just any basis. It is an orthonormal basis for R2 cross 2. Okay. The next one was these two matrices of this form. Matrix of this form. Okay. Where A, B, C, D are real numbers. Okay. The question was if this is the subspace of R, if this was a subspace of R2 cross 2, and if M is QW subspace of R. How do you verify? What is the definition of a subspace? Okay, it's a subset. Are these subsets of R2 cross 2? Yeah, these are 2 cross 2 matrices. So, and this should also be a vector. How do you verify if it's a vector space? Yeah, so if you take any element from here, you will get alpha A, alpha B, alpha C. This, what you started with was a symmetric matrix. This is also symmetric because these two elements are the same. Okay, that means if you scale by, if you do scalar multiplication of a symmetric matrix, what comes out is also symmetric. If you have two matrices A1, C1, if you add these two, what will come out will still be symmetric. That means the set of symmetric matrices, symmetric 2 cross 2 matrices are closed under scalar multiplication and vector addition. That means this is a subspace. You can similarly show that this is also a subspace. Okay. Is that clear? And then the next question was on what are orthogonal complements of a vector space? What are orthogonal complements? Sorry? You'll have to be louder. I don't. Hey, what is UV? You have to first. Okay. So let's say we have a parent space V. And then what? And then you have two subspaces U1, U2 that are subspaces of V. And then what? So U1 is perpendicular. What does this mean? No, I know when two vectors are perpendicular. What does it mean to say a subspace is perpendicular to another subspace? No. It, okay. So you're saying if you take some element U1 that belongs to set U1 belongs to U2, then U1, if all possible U1, U2 are orthogonal to each other. Okay. I don't want to add to your confusion. Let me not write this. Okay. I'll simply say U1, U2 for all. But that's not enough though. This just means the subspace U1 is orthogonal to subspace U2. It does not mean it's an orthogonal complement. Okay. So you're saying U1, but this is anyway true in this case, right? If they're orthogonal to each other, this is anyway true. But that's not, I mean, this is included in this, so we don't have to say it. Okay. Belongs to it. Okay. Okay. What does it mean to add two subspaces? I understand adding two vectors. What does it mean to add two subspaces? See, the point of the midterm was to essentially test, make sure you guys had all this on your in your fingertips. That's really important. What is the definition of the sum of two subspaces? Maybe you're correct. You might already know what is this. What is the definition? When do you, if you add two subspaces, do you get a subspace? Okay, but how do you generate that subspace? Okay, so elements of this with itself, is it? No. Okay, so if you take, let's say U1 is U1 vectors are elements from U, the subset U1, U2 are elements from this, then you're saying V is simply set of all, yeah, sum of all vectors with one vector coming from U1, another vector coming from U2, and all possible sum of all possible combinations. And if that gives you V, then you say U1 and U2 are orthogonal complements, and you can write like this. Okay. Then the question is, okay, these two are subspaces of R2 cross 2. Are they, so the question is, do they form orthogonal complements? How would we verify that? Yeah. Sorry. Hey, hold on. Here, this is the issue. Okay, inner product, right? But what is the inner product for this space? See, okay, when we talk about this as being the standard inner product, this is the standard inner product only for Rn. In fact, this is not even the standard inner product for Cn. What is the standard inner product for Cn? Right? So every time you have a vector space, you have to define what the standard inner product is. And here in the question, I've said the standard inner product is this weird angular bracket stuff that gives me a real number. I said this is the standard inner product. So now, if you're talking about orthogonality, then you check for orthogonality with respect to the standard inner product, like we did for the previous question, where you had to find out that this was an orthonormal basis. This one. Now I come back to the question: how do we now verify that M symmetric and M skew symmetric are orthogonal complements of R2 cross 2? Again, blindly go back to the definition. Okay, if they are orthogonal complements, what conditions do they have to satisfy? Here, we just talked about it, right? the subspace M symmetric should be orthogonal to subspace M skew symmetric. How do we verify if they are orthogonal? If an element, so that means if you take any element from M sim and any element from M skew symmetric, and if you take their standard inner product, which is defined previously, do you get zero? Okay. All right. So now, that means if we compute the standard inner product A B B C 0 D minus D, what do we get? Okay. A into 0, we got D minus B dot D plus C dot 0. That is 0. So it looks like in in the vector space 2 cross 2, symmetric matrices are orthogonal to skew symmetric matrices. Okay, so at least the first one is satisfied. So this is okay. This is okay. Okay. What about the next one? This just says that they're orthogonal. The subspaces are orthogonal to each other. What is the next thing we have to verify? The first one is okay. So we know that M sim is perpendicular to M is KW. Right. Now we have to show that the sum of those two matrix subspaces covers all of our 2 cross 2. Okay. How do we show this? Well, let's see what happens. This is an element from our this is a symmetric matrix. This is a skew symmetric matrix. If you add these two, what do you get? You get A, you get C, and then you get B, not into. Okay. It's not immediately clear if this is. You could, for example, if I gave you an arbitrary matrix, if you can find A, B, D, A, B, C, D, such that if you add all of them together, you get. I mean, if you arrange them like this, you get this. Or maybe you can, but you'll have to show it. You remember when we said any square matrix can be written as a sum of what? Sum of a symmetric matrix and a skew symmetric matrix. Well, these are symmetric matrices, these are skew symmetric matrices. That means if I can write any matrix as a sum of a symmetric and a skew symmetric matrix, this applies for 2 cross 2 matrices. And this symmetric component simply comes from M sim. The skew symmetric component comes from, that means the sum of M symmetric and M skew symmetric is in fact all of R2 cross 2. Okay, so in fact, this is equal to this is any arbitrary matrix. So if you're given any arbitrary matrix, you can always find these 4 numbers which correspond to these 2 matrices, such that your M sim plus M skew is in fact equals to. Okay. Is that clear? Okay. See, the next question was about, okay, this is a subspace of R2 cross 2. This is a subspace. Our goal was to find an orthonormal basis for this subspace and for this subspace. And the hint was that you could use that E. Um, how do you come up with an orthonormal basis for this? What do we mean by orthonormal basis? When I say orthonormal basis for MSIM, what do I mean? not MSIM, no. This is a subspace. I'm talking about an orthonormal basis for this subspace. So let's say I'll call that set B. Okay. It has some elements. What properties does this have to satisfy? Right. Okay. Well, let's start with, if it has to be a basis, then this has to be a linearly independent set. And it has to span. That means if I take the linear combination of this, or if I take the span of the set, it should give me all possible symmetric 2 cross 2 matrices. Okay. In addition, that's just basis. In addition to that, the elements have to be orthogonal to each other and they have to have length 1. Okay. Now, how do we come up with a, uh, an orthonormal basis for this? Again, using these 4 matrices. See, you have to produce simply this. There is no standard, there is no algorithmic way of doing this. Okay, you simply have to look and be a little creative. That's all. Exactly. If you take A into the first matrix, then you will get A 0 0 0. So I get A 0 0 0. If you do C times the last matrix, then you get 0 0 0 C. Okay. So you're saying B 0 B 0 0 right? 0 0 B 0. Fine. Now, so what are the basis elements of the basis? Okay. Let's see. This you're saying this is a basis. This is an element of the basis set. Okay. And well, let's just do it like this. Maybe it's all of this. Mhm. Maybe this is a basis. Okay, because the span of this will give me all symmetric matrices. Will it give me all symmetric matrices? Well, is it a linearly independent set? It is a linearly independent set. Okay. Does the span of this give me all symmetric matrices? It does. Okay. Okay. Let me do this. Alpha times A0 0 0 plus alpha 1. Alpha 2 times 0 B 0 0. Does that give me a symmetric matrix? It won't, right? Because the uh, well, top right element will be alpha to B, bottom will be alpha. It's not. So this cannot. The span is in fact R2 cross 2. It's not to the subspace. So we have to change something. What if you change it like this? You don't separate that into 2 matrices. You simply keep it as one matrix, and you remove one element here, and you say this has to be B. Then this is out. This is B. Now this will always give me a symmetric matrix. In fact, even if these two are 0, this is a symmetric matrix because these are the same. Similarly, if everything else is 0, this is non-zero. This is still symmetric. So this in fact gives me the span of this, gives me all possible symmetric matrices. But that's just a basis. It's not orthonormal. What do we do? Normalize it. Okay. What will this become if you normalize it? 1 by 1 by 2a, is it? Or, oh, will it be root a? Why will it be root a? It will be 1. Because if it's 1 by root a, hmm, what this? What about this one? If, well, this won't work because what is the length of this? Length of this is 2. So what do we do? Well, square of the length of this is 2. Well, exactly. You simply divide it by 1 by root 2. That's it. Okay. This is now an orthonormal basis for this. What about this? Can you tell me a basis for a skew symmetric matrix using the same logic as here? Okay. 0, 1, 0. It's fine. If you now multiply this by any scalar, get all possible 2 cross 2. All right. Now this leads to the next question. What is the dimension of the M subspace M symmetric? What is the dimension of a subspace? Number of? Hey, no, not rows and columns. Rows and columns come in when we are dealing with matrices. Don't think of this as, I mean, it is a matrix, but think of this as an element from a vector space. Well, if it's a basis set, it's already linearly independent. So you don't have to say number of independent. It's simply the number of in the basis, right? How many elements does the basis of M sim have? 3. That means the dimension of this is actually 3. And what is the dimension of this? 1. Okay. And what is the dimension of R2 cross 2? 4. Because this is 4. Okay. And of course, that makes sense because the sum of the dimensions of the individual or orthogonal subspaces that are orthogonal complements should equal to the dimension of the entire vector space. Okay, I hope that's clear. Sorry, I forgot that eigenvalues were not part of the exam. So in case I've not given you 3 marks for the problem, let me know. I'll give you 3, no problem, even if you got it wrong. Okay, all right. The last one, the problem was to find all possible left inverses of, right? Yeah. How do we find, what is the definition of a left inverse for this matrix? Okay. Let's say B is a left inverse. Then I pre-multiply A by B. And what am I supposed to get? In this case, yeah, it's 1 cross 1. Okay. Now, how do we find all possible B's now? How many B's do we have that will give you 1 if you pre-multiply it by A? Well, pre-multiply it or pre-multiply A by that matrix. Is there only one matrix that does it? No. What do you mean by many possible? Is it 3? Is it 100? Okay, there are infinitely many, no? Infinitely many. left inverses. How do we find them? Mhm. Okay, let's just do this. Let's say how many elements does B have? Three. Let's call it B1, B2, B3. And if B into A is to give me 1, then that means B1 plus 2 B2 plus 2 B3 equals 1. There are three unknowns, one equation. So two of them are to be free variables, right? So you simply say, okay, I'm going to let B1 be anything. I'm going to let B2 be anything. Then that means B3 is 1 minus B1 minus 2 B2 divided by 2. Right? That means any matrix of this form, B1, B2, 1 minus B1 minus 2B2 by 2 will give me 1. If I multiply here, A, it'll give me 1 because here B1 plus B2 into 2 times this is gone. These two get cancelled. Well, this is, hold on. I've done a mistake somewhere. What mistake did I do? 1 minus 2B2. Ah, yeah, here, sorry. If you multiply it by A, B1 plus 2B2 into 2 times this is gone, and then it's fine. So this is the set. So this is essentially the, so where B1, B2, if you choose any real numbers for B1 and B2, all matrices of this form will be left inverses for A. See, this again was a freebie problem because this is a problem like this is there in the slides. So everybody should have gotten 3 for this. See, I hope that you've now identified at least things where maybe your own understanding of the material is a little weaker. So please go back and revise. And again, these definitions like what is a vector subspace, what are orthogonal complements, these you have to be sure by now. Okay. Right. And again, don't think this material is gone now. This will never come back. You never know. This might come back for your midterm and other things because this is really fundamental. Yeah. So don't treat this as this is done and dusted. I only have to focus on the rest of the material. See, in fact, I did not get into things like rank of a matrix and all that in the midterm, which is again a very important topic for the things that we'll discuss moving forward. So again, please make sure you revise all that. And again, always carry that sheet with you because if you've forgotten the definition, just look up the sheet and then that will probably help you. Okay. Are there any other questions about the midterm? No? Okay. All right. Then we move on to the next module. Okay, on a very important topic on singular value decision. Okay. Right. See, what is it? Maybe two classes, two modules before, not the previous module, but the one before that, we talked about eigenvalues and eigenvectors, right? And the motivation for that was we said, well, we know that vectors are, well, the representation of vectors depends on the basis that you choose. And in fact, we found that when you're talking about matrices, which can be thought of as a map from, well, a linear map from Rp to Rq, this is what is the size of the matrix? If it maps from Q to P. P cross Q. Matrices represent linear maps from RQ to RP, especially matrices that are P cross Q in size. We said, in fact, it's not just the vectors that are basis dependent. If you want to represent linear transformations through in the form of matrices, the matrices are also basis dependent, right? Now, if A is the representation of a linear transformation in the standard basis, what is the corresponding representation of this linear transformation in the V basis? And let's, for now, let's say we are restricting our attention to only n cross n matrices. And if I'm restricting my attention to n cross n matrices, this is A represents a map from Rn to Rn. And if V is a basis for Rn, how many elements does V have? And see, by now you should confidently say there are n elements, right? And those are V1, V2, Vn. And each of these is an element of Rn. Okay. Okay. If now A is the representation of this map in the standard basis, what is the corresponding representation in the V basis? AV. Well, I want the representation of this linear transformation. Given that I know it's the representation of this linear transformation in the standard basis, and the basis that I'm interested in switching to is V. P into, is that correct? Well, that is the only possibility. I don't know which one is correct. You have to convince me which one is correct. There are these two possibilities. Which one? First one or second one? First one. No, this is not the one. See, here, if this is the representation of the linear transformation in the V basis, what goes in is in the V basis, what comes out is in the V basis. Okay. What does V inverse do? What is the interpretation of V inverse? The inverse of this one. Change the basis from what to what? Right. So this changes things from the standard basis to the V basis. So if this was correct, what needs to go in has to come from the standard basis. So this cannot be right. A only wants things in the standard basis. What this will give me is the V basis. So this is wrong. So this is in fact inverse A V. Okay, and what are A and AV called? Are similar matrices. And this is called what transformation? Similarity transformation. Okay. All right. Now I have maybe I have another challenge. Okay. Let's say I want to do something weird. I don't want to work just with the V basis. I want to work with the V basis and a W basis. Okay. This is also a basis for Rn. Okay. And the elements are of the set, and I have n of them, and each Wi is Rn. Okay. I want this weird representation where the input to my linear transformation come from the V basis, but I want the outputs in the W basis. Is that clear? A takes stuff in standard basis, gives in standard basis. AV takes synthesis. This is in VV. What I want is this. I want A WV. W is output, V is input. What goes in has to be in the V basis. What comes out has to be in the W basis. Can I obtain something like this? Given that I know A, I know the V basis and the W basis. How do we find out A, W, V in terms of A? What goes on first? Sorry, let's start. Where do you want to start from? Leftmost or the rightmost? Or the right? Is this the leftmost? Okay. Okay, we'll start from V, is it? Okay. Is that right? This is V inverse. Well, just use the logic there. What is the logic there? Sorry. No, it cannot be like this. Okay. Okay. What is V inverse converts? What this type of conversion does? Standard to V, right? Standard to V. Okay. What does V do? What conversion does V perform? V basis to standard basis. So this is correct, no? What goes in is in the V basis, so that's okay. What comes out is in the standard basis. A works only with the standard basis. What comes out is in the standard basis. And W converts things from the standard basis to the W basis. So this is correct. Yeah? Okay. Right. So now if you have something like this, well, we don't have to restrict ourselves to just this one basis V that we have to work with. We can now do all sorts of fancy stuff. Okay. In fact, I'll leave it as an exercise for you. If you don't have A, if you had AV, what would be AWV in terms of AV? Okay. You can think about it, that later, not now. Okay. See if we can do this, and I'm happy to work with two completely different bases here. Then we don't have to see here when we talked about this similarity transformation. We said we restricted ourselves to this mapping from Rn to Rn. But if we are willing to work with two completely different bases, then we don't have to restrict our A to be n cross n matrix. In fact, now I can talk about any general A, that's P cross Q. This is a map from RQ to RP. Okay? And let's say the and these are not the same basis. That means here I cannot say I want to, I don't have a common basis for the two of them because these are two completely different spaces. And A is the representation of the linear transformation from RQ to RP, where the input vectors are all represented in the standard basis for RQ, and the output vectors are all represented in the standard basis for RP. Okay, and that's A. Okay, but instead, if I want to work with the Q basis in RQ and the P basis in RP, my question is now what is the corresponding A, P, Q? Well, it's just that it's AQ. My inputs are in the Q basis, outputs are in P basis. That's just this. And now, whereas similarity transformation only work with mappings from Rn to Rn, this type of a mapping or this type of a transformation can be applied for any rectangular matrix. Okay, and in there AV and A were called similar matrices. Here, these two are called equivalent matrices. Okay. See, in fact, we started talking about this idea of similarity transformation because uh, we were asking the question, uh, if there are simpler representations for my linear transformation than what I get with A, right? Because in general, if you have a linear transformation, what geometric operations does that linear transformation perform? Yes, it performs scaling, it rotates, and it also can reflect. Okay, but if you have an A that is Rn to Rn, and A is diagonalizable, no, then you get a very simple representation for A. Okay, let's assume V1, V2, Vn are the eigenvectors of A. A and lambda 1, lambda 2, lambda n are the eigenvalues of A. What is the corresponding similar matrix for A in terms of the eigenvector basis? Sorry, did I say similar vector? I'm sorry. What is the corresponding, what is the similar matrix to A in terms of the eigenvector basis? Well, if you are going to work with the eigenvector basis, then the similar matrix is a diagonal matrix, okay, which is simply lambda 1, lambda 2, lambda n. And how do I obtain this from A? Well, this is the representation of A in the eigenvector basis. Then it's V inverse. That's all, right? So if we are talking about um, linear maps from Rn to Rn, and if you're talking about maps that can be diagonalized, then if you do uh, diagonalize, then if you look at the linear transformation, the representation of the linear transformation in the eigenvector basis, then you have a very simple representation. Okay. Now the question is, can we extend this to general maps? This was only applicable, the eigen decomposition was applicable only for matrices that were square, matrices and matrices that were diagonalizable. If it's not diagonalizable, then you don't get a diagonal matrix, then you get what is the Jordan form. Right? Now the question is, okay, that's for these restricted sets. Is there something that we can do for, is there a similar form where a linear transformation represented by A in the standard basis has a simpler representation if you choose some other basis Q and P? Okay. And in fact, that leads us to what is the singular value decomposition. And it's kind of a very surprising result, a very useful result. And it turns out, and if it's general, there is no, every matrix can be simplified or diagonalized. Okay. I'll, I'll write it down and then we'll talk about what these are. Any matrix A, it doesn't matter what kind of matrix it is, square, rectangle, doesn't matter. Okay. Every matrix A can be written down like this, and this decomposition is called singular value decomposition. That's SVD. Okay. Let's say A is E cross Q. Okay. U will be E cross P. V Q cross Q. This will be in fact, Let me write this down. Write this the other way around. A equals A V no EQ Q inverse no. Yeah, that's right. Inverse. This is P cross Q. This is P cross Q. What is the size of this? This matrix P cross P, because it's a basis for RP. And you see that this has that flavor, where the inverse is replaced by transpose. When can you replace the inverse by a transpose? Yes, when the matrix, if you are working with the orthonormal basis, okay? If you have an orthonormal basis for RQ, then the matrix that is formed by uh, taking the basis vectors and putting them in the columns, you get an orthonormal, no, sorry, you get an orthogonal matrix. Then you can transpose. And here, U and V, these are orthogonal matrices. Cis, okay. And sigma is diagonal, but this is a square matrix. So this is not a square matrix. So what that means is it can be written like this. This is a diagonal matrix, and these are block zero. Depending on the shape, you might either have this, might have this, or you might have this. But the general form is like this. Okay. And D is a simple diagonal matrix. Okay. See what if U and V are orthogonal matrices? That means what does it say about the basis for RP and basis for RQ? Well, the columns of U will form a basis for RP. The columns of U will be an orthonormal basis for the rows of V will form a orthonormal basis for RP. And let's assume the rank of A. What is the rank of a matrix? Span of column of A, right? Okay. Or it is the number of independent columns of A. If the rank is R, right, then it turns out that this matrix sigma is of this form. This will be of size P cross Q. D 0, 0, 0. D will simply be a R cross R matrix, and D will be equal to, D is usually written like this: sigma 1, sigma 2, sigma R, where sigma I is a real number. And the convention is the order in which you write them is like this: sigma 1 is greater than or equal to. See, what this means, if you're talking about this mapping from RQ to RP, you can find an orthonormal basis for RQ and an orthonormal basis for RP, such that the representation of the linear transformation, if you decide to work with these two bases, has a diagonal expression. That is an interesting result, or maybe a surprising result as well. Because when we were talking about eigenvalue decomposition, you had all these restrictions. It had to be square, it had to be diagonalizable and all that. Whereas this one shows now you can diagonalize any matrix, in fact. We'll simply look at a little bit more about what these U, sigma, V are. Okay. U is called, I keep forgetting, I think this is called the left or here. U is simply a matrix like this. U1, U2, U, E. Okay. And these are called the left vectors. Okay. And these are nothing but the eigenvectors of A, A transpose. Okay. Because if you substitute for A using a singular value decomposition here, what you will find that this will be equal to, well, what will this be equal to? You can tell me. Assuming A is equal to this. What is this equal to? Oh, no, no, no. It will not be equal to I. Why will it be I? V transpose. What is this? If you take the transpose inside, no. V sigma transpose is, well, okay. Well, what is this? I, because it's an orthogonal matrix. So this is simply okay. What will this be? We can't write it as sigma square because what if it's a rectangular? If it's a rectangular matrix, you can't do sigma square. What will that? Hey, why will that be equal to I? Sigma is that, right? So what will you get if you do sigma transpose? I will remove. Well, what do I remove? I remove this. It's fine. I remove this. I'll remove this. What is sigma transpose if sigma is the P cross Q matrix of this form? Sorry? Ah, okay. Sigma transpose will be equal to, you can verify this. Okay. So I will replace this. Is this a symmetric matrix? A transpose? How do you check if it's symmetric? What is this equal to? Yeah, so this is symmetric. Okay. What do we know about and symmetric matrices are always diagonalizable. Okay. What do we know about the eigenvalues of a symmetric matrix? Do you remember? They're always real. What about the eigenvectors? Yes, it's diagonal. I mean, that's what I meant by diagonalizable. The eigenvectors form a orthonormal basis. Okay. What we've written down here is simply the eigen decomposition of this because here these are orthogonal matrices. This is diagonal. Okay. So what I'm trying to get at is the left singular vectors are simply the eigenvectors of A transpose. Okay. And D square, What will be d square? What will be the elements of d square? Sigma 1 square, sigma r square, sigma 1 square, sigma. These are simply the eigenvalues of A transpose. Okay. Now, we know this is symmetric. Is this positive definite, positive semi-definite, or we don't know? This is positive semi-definite. Why? Yes. These are real. And if you square them, it has to be a positive number. So it is positive definite or semi-definite? Here, it is semi-definite because only R of these values are non-zero, rest are zero. So this is a positive semi-definite matrix. And if you look at A transpose A, what will we get? If you do this, you will find this is V sigma transpose, sigma E transpose, and V, which V, which is simply V1, V2, VQ. These are mm, and these are simply the eigenvectors of A transpose A. And this again will be in fact this we probably did not discuss in class. If you have a matrix A and A transpose will have common eigenvalues. Okay, they'll have the same eigenvalues. Well, here I'm talking about square matrices. A and A transpose will have the same eigenvalues. In fact, yeah. Okay, I will stop here for today because we are out of time. We'll continue this tomorrow. Are there any questions so far? Yes. If you have questions about the answer sheet, you can come and ask me tomorrow. Yeah. So you have time till tomorrow evening to clarify. And if it's related to question 13, the eigenvector eigenvalue problem, you can simply meet the TAs, and if you've not gotten 3, we'll give you 3. Thank you. Thank you.